So, this is some aspects. Now, we will look into some aspects, then some more we will look into when it comes. Now, in thermal design of building or energy efficient building design of building, the decision variables are envelope parameters, which I have discussed so far. Orientation is the other one, shape, type of glass and the fenestration location. Shading devices, I will discuss some of them. These are the decision variables, and you want to find out the best combination. You can use some sort of optimization process, for example, evolutionary algorithm of the kind of genetic algorithm, etc. But then you must have a method for estimating the quantum of heat coming in. One such method is what we call admittance method. I am not obviously going to go into the mathematics of it. There are other methods like there are numerical methods one can use for calculating the heat transfer, finite element, finite difference, and there are some other kind of solutions. Many software might be using them, like time domain solution of heat transfer equation for a periodic wave outside. So, etc., etc. So, this there are methods. So, one can use them. Now, if you look at design, as I said, first is a natural perturbation, which could be yearly variation or diurnal variation. Then I can actually modify my surrounding of the building. For example, plant a lot of trees, etc., right, have lot of surfaces through which water can percolate and evaporation occurs. So, these are called microclimatic control. These are called microclimatic control. So, I can in the city planning, urban planning, in fact, all aspects of functional planning or functional design of building starts from urban planning, including energy efficient building design. So, to start with, you can see that surrounding and temperature, surrounding temperature and humidity of the environment is modified, somewhat less variation will be there by microclimatic control. Then you might use passive part or envelope system and overall thermal energy efficient building design of the building, passive design of the building. But if you want 100% control, then you need mechanical. So, mechanical conditioning, air conditioner, etc., you might need. So, that is what I was just talking earlier also. This is the external diurnal variation, this is with some sort of construction, a better construction brings it there, but you want within this small portion, then you have to use active system. Some aspects of microclimatic control, some you can model them. For example, this was a case where we did model the Humayun's tomb, where there are a lot of trees, and this is vis-a-vis another place, another weather station whose data was available to us. This data was measured by us in a project and this was available to us. And then this had got a lot of trees, as you can see, lot of trees here, while this did not have, right. This is a weather station, Safdarjung Airport in Delhi, and this is the case, and then these trees can be thought of as hemispherical bodies, green bodies. So, one could calculate and model them and calculate, and one would see both by measurement as well as computation that actually temperature in this zone, this place is much lower than the temperature of the measured temperature of the other place, that Safdarjung Airport or weather station I talked about. And by modeling also one could see that. So, in other words, what I am trying to point out is that you can modify the surrounding environment of the building, bring down the temperature, but remember it increases the relative humidity. So, it increases the relative humidity obviously, because a lot of evaporation occurs from the green trees, etc., but one can modify this. So, that is the first level. So, variation can be controlled somewhat if judiciously done. So, that is the microclimatic aspects. In this case, of course, there are a number of trees, etc., are given, but I am not really interested in the modeling part of it. So, let us see now in envelope part, how do we select different types of envelope element. Now, in hot dry desert climate, this is shown for a this is shown for a east wall, right. This is shown for east wall, Now, in east, this is the diurnal variation, daily variation of temperature, right, and a east wall receives maximum radiation in the morning. Now, if you can see, this is the comfort zone, this is actually my desirable zone, actually comfort zone is, sorry, this is the comfort zone, and early in the morning about 6 am or so, or rather late in the night onwards to early in the morning, in a hot dry desert climate, it can be quite cold outside, because a lot of radiation, solar radiation, a lot of long wave radiation would have been there from the surface of the earth to the external sky. So, temperature comes down, diurnal variation is high. So, this is the typical temperature variation, this is the typical temperature variation, right. And if I superimpose the east surface solar radiation, east surface receives maximum solar radiation in the morning, and after 12, the sun goes to the south in northern hemisphere. So, what this becomes cold after night, in the night it is cold. So, if I can design my wall in such a manner that the peak heat, this one reaches, this peak heat is shifted by 14 hours. In other words, at the outside peak temperature is around 8 am, 9 am or 10 am, but inside the maximum heat, peak of the heat dissipation or heat intrusion into the space, internal space is somewhere around maybe 12 o'clock in the night, or 11 o'clock in the night or something of that kind, which means that I require 14 hours of time lag, 14 hours of time lag. Such examples I can have some more. Same hot dry desert climate, this is for a west wall, because the west wall same temperature variation is like this, but the radiation received, peak radiation would come only in the afternoon. So, so I need only 6 hours of time lag, because this is the time when I need the heat to come in to make it comfortable, because inside becomes cold by that time. So, I see that the peak heat transfer at the internal surface of the room should take place in the west wall after 6 hours only. So, I provide 6 hours time lag, right. And for roof at 12 noon or near that, the peak is there. So, I need around 9.5 hours or something like that. This is an example how I can choose the wall element. Now, to have high time lag on the east wall, I need heavy wall, density as well as specific, right, and also length. So, I can provide, we can design, I am just saying, you cannot design a non-uniform wall system, but judiciously one can think about it. Now, this is quick understanding of this, and we got to understand a little bit of solar radiation related issues. There are different angles, something called an altitude angle of the sun. So, sun's position in the sky is defined by two angles. For example, if this is my sun, so this angle we call as altitude angle, there is something else we call as azimuth angle. So, its position, it is measured in a kind of a spherical scenario. So, you have an angle measured, let us say, from north, right, so position of the sun, or you might measure even from the south, south depending upon which hemisphere part of the, like which convention you are using. So, if you use from north, this is what up to the projection of the sun's path onto the ground, that the angle between north or your reference line, reference direction to that line we call it azimuth, and the angle in the vertical plane from its projection onto the ground, that we call as altitude angle of the sun. So, sun's position is defined by these two angles, right, and wall's position is also defined by two angles. One we call as tilt angle, depending upon if it is inclined or if it is vertical, the tilt angle is actually 90 degree, right. And if I draw a normal to the wall, then its wall azimuth will be the normal angle between my reference line and this normal to the wall, that is called wall azimuth. And we define something called wall solar azimuth, which is the angle between normal to the wall and sun's projection on the ground. Now, these angles are important if you are doing some calculation. I just thought I will give an introduction to this. So, azimuth angle of the wall, azimuth angle of the sun, this is again shown with respect to south. Here it is showing this is the azimuth angle of the sun, and this is the altitude angle of the sun, solar altitude. One may follow from geographical north to angle clockwise, geographical north from geographical north to the sun's projection on the ground. The once consistently any convention followed must be consistently followed throughout the analysis. That's what is important. So both this sort of thing is done. For example, here it is clockwise from the north. This is your azimuth angle Z, and this is called altitude angle. Is this one is the altitude angle. So this gives you an understanding of what these angles are. They are important. I think so azimuth angle is angle between the sun's ray projected on horizontal surface with a reference line from true north measured clockwise, may be one of the convention. In northern hemisphere, people would prefer to do that. Altitude angle is the angle between sun ray and its projection onto the horizontal surface, and wall azimuth is the angle between reference and projection of normal to wall on horizontal surface, right. So that's what it is. And incident angle is the angle between sun ray and normal to the wall, that is called incident angle, right. Wall solar azimuth is the angle between projection to normal to the wall on horizontal surface and sun's ray projected on horizontal plane, which I just mentioned a few minutes before, and again is coming in written form, right, is coming in written form. So for horizontal surface, one can find out the radiation, what we call beam radiation is the normal to the beam direction. So sun's rays, say this is my sun ray, and the beam radiation is normal to a surface which is normal to the beam direction. And you can find out if I have incident angle, which is the angle between normal to this surface and the sun's radiation, this is called incident angle. Then this is obviously the altitude angle, this is IH is the incident angle for the horizontal surface. So one can find out the radiation received here is IB cos I, less because normal surface radiation density would be more, watt per meter square would be higher, but on this surface it will be less, it has the same energy, gets distributed more. So it is IB cos IH, where IH is the incident angle, which is nothing but sin beta, altitude angle for horizontal surface. Vertical surface, each vertical surface one can calculate out, but I do not think I will go into details of this too much. So measurement is usually done on horizontal surface, therefore beam radiation can be calculated backward from knowledge of radiation received on horizontal surface. For any other surface, actually you can find out with cos I, and IH cos I by I sin beta. So that is what it is. Okay. The sun's position is defined by two angles, I said, but sun's position actually changes from day to day, because earth has got a banking of 66 point whatever degrees, 23.5 and 66.5. So earth is inclined, it moves like that, it makes an angle with the plane of its revolution about the sun, and therefore the normal sun's radiation in summer falls on Tropic of Cancer, it is normally, and in winter it is Tropic of Capricorn. I mean, I will not say summer and winter, for northern hemisphere I am saying summer and winter, or if I may put it that way, it is around December 25th, around that around that time sun's radiation, winter solstice, during on which sun's radiation falls normal onto the Tropic of Capricorn, while in June it falls on Tropic of Cancer. So and in between it falls on equatorial plane, right, equinoxes, which we call equinox. I do not think I will go too much into this. So you can see that sun's angle of the sun's radiation falling on a given position is not same, right. It may be normal on equator, actually sun's radiation falls normal between minus 23.5 to plus 23.5, and its angle with the equatorial plane varies, sun's radiation, direct radiation, it varies, and we call this angle as declination. I do not think I will go into details of this, it will take longer time to explain. So, if I take a look at any point on the surface of the earth, the sun's at 12 noon, sun's altitude angle at 12 noon, it would vary depending upon the day of the year. Now, declination is the angle between equatorial plane and sun's direction of sun's radiation. Maybe I have a better diagram to explain this. Sun's radiation, and this is the this is the sun's rays, right, and this is the equatorial plane, this is the equatorial plane. The angle made between these two, we call it declination. Angle made between these 2 points is called declination, right. This is the north direction on which the earth rotates. It is always permanently inclined, as I said, to the plane of its revolution, and this might be my point. Okay. So, this is related to declination, is that angle. So, altitude and azimuth angle of the sun will depend upon declination. It will also depend upon time of the day, right, and also latitude of the place. So, if this is the earth, if this is the direction of the sun, I think this is a simpler diagram to explain for a short period of time. This is the equatorial plane, this angle we call it declination angle, and if I have a point somewhere there, this is the point, right, this is the latitude, this is the point I am point of my interest, this is the latitude. Latitude is the angle made at any chord circle, right. The angle, this angle we call it. So, at equatorial latitude is 0, and as we go up north pole it will be plus 90, south pole it will be minus 90, or you can call 90 degree north or 90 degree south. So, in India actually it is 8 degree north to about 32 degree north latitude. Thiruvananthapuram is 8 degree or somewhere close to that places, and Ladakh or Leh would be somewhere around 32 or close to that. So, we belong to northern hemisphere with this kind of latitude. Now, one can actually find out the angles and calculations and formulae, which I am not interested at the moment, right. So, when you do thermal design, therefore, this radiation calculations becomes important, and one can do that. Now, in order to find out the best orientation, a simple method has been given in SP 41. I find out, because if I orient this in northern hemisphere, sun goes from east, and then the sun's radiation is received onto the south surface, and then goes to the west, right. West surface will also receive some radiation in the afternoon, and the altitude angle of the sun in summer is very high, while in winter it is much less, right. So, therefore, if you have something facing north, it will not receive any radiation, and if you want to find out depending upon the orientation. So, large surface, supposing depending, this is my surface, this is the plan of the building, let us say, this is my north direction, this is my south direction. Now, I change the plan to this one, long axis parallel to east, north and south, here it is parallel to east and west. So, the orientation change is occurring. In that case, this will not receive any radiation, larger surface will not receive any radiation. This will receive radiation in winter, but summer it will receive much less radiation. This receives radiation in the morning, this receives radiation in the afternoon. So, orientation has got a role to play. Shape has got also a role to play, because aspect ratio, if it is square, it will not matter, the orientation will not matter. One simple way of finding out the best orientation is given in SP 41, the standard publication, the special publication of Bureau of Indian Standard related to energy efficient, functional design of building other than what is called industrial building. What it says is minimize twice summer gain minus winter gain. I mean, it does not say that, but I am saying the philosophy would be minimize twice summer gain minus winter gain. Why twice? Because cooling is always costlier. It could be 3 to 4 times costlier than heating, right. So, if I choose a plan which will have high winter gain, that is actually good for me. So, I would like to minimize this function, but summer gain I would like to reduce. So, minimize summer gain minus winter gain, that would be a good orientation, good design. But then I put a weightage factor at least 2 here, because if more I minimize the summer gain, more I reduce the summer gain, I will save onto the cost. So, for an energy efficiency, this is a good idea. So, for an envelope A1 to AN surfaces, let us say walls, roof won't matter as far as orientation is concerned, as long as my floor coverage is same. So, A1 to AN surfaces, you find out the radiation intensity on that surface, vertical wall surface, multiplied by the corresponding area, that will give you total radiation, it will give you the total radiation. Take one representative summer day and one representative winter day. The code SP 41 takes 16th May and 22nd December. This is a winter day, this is a summer day, right. And it says you find out the sum total of heat gain minus the winter shading, and although code, this is not from the code, but I am saying it is a good way to possibly find out, calculate out the solar radiation received onto the whole building, that is I into A for the whole building on 16th May and also on 22nd December, and find out this quantity. Whichever orientation gives you minimum, that is the best. So, if you are manually quickly doing it, you can do it, right. Manually you can quickly do it in this manner. In fact, SP 41 gives you tables of radiation on different surfaces for certain latitudes, but you can calculate out in the formula. I did not give you those formula, of course, in this lecture. So, basic formula is something like this. If there are n walls, summer gain will be IT, summer gain, and winter loss, and you actually sum total of summer gain minus winter loss, twice summer gain minus winter loss, you can minimize.